A timber building standing for over 900 years in one of the wettest climates on Earth, still solid and still dry. That's the Stave church in Norway. And its secret is Rainscreen facade. Fast forward to today, we are building timber skyscrapers 18 stories high. And one thing keeping them safe from the weather is again a Rainscreen. This system has protected buildings for centuries. It works in freezing winters, it works in tropical downpours, it works in salt-laden coastal winds. So why does it have such a bad reputation? Well, Grenfell Tower, Campanar building in Valencia, and the Torch Tower in Dubai. These are the tragedies where Rainscreen played a part. But here's the truth, Rainscreen cladding is not the villain. When it's designed and built properly, it's one of the most reliable, adaptable, and long-lasting ways to protect a building. My name is Eugene Korch, and I'm practicing facade engineer, and I teach facade engineering at the Institute for Architectural Science and Technology. In the next 25 minutes, I will show you why Rainscreens work, from ancient timber churches to modern timber skyscrapers, from Roman engineering to modern building science. And yes, we'll talk about the disasters and the lessons they've taught us. Before we dive into history, let's define what we are talking about. There are many definitions of Rainscreens, but almost all share two key words: cavity and water. In simple terms, a Rainscreen is a wall system that uses cavity to manage water. It's a multi-layer assembly where each part plays a specific role. Here's the most common example, starting from the inside out. First, the internal finish. Often painted gypsum board or decorative panels. Next, the backing wall. This might be concrete, masonry, or a stud wall with sheathing made from light steel or timber studs. The backing wall supports everything that follows. Over that, we install a weather-resistive barrier. This membrane blocks air and water infiltration. Then comes continuous insulation. This layer controls heat transfer and boosts energy efficiency. Now the crucial part, the cavity. A ventilated space that allows air to move and water to drain away. Finally, the cladding, the outer skin that takes the brunt of the weather. Here's how it works. The cladding does not need to be watertight. If rain gets through, it hits the cavity. Wind pressure cannot push it across the gap. The water drains down and exits at the bottom. Any leftover moisture dries out through ventilation. These walls are everywhere. You'll find them in every climate, culture, and political system. And this isn't a new idea. It's been protecting buildings for more than 2,000 years. The most refined version is so-called perfect wall. The most common and robust example is a solid concrete or masonry backing wall, a water-resistive barrier, often building paper or bread membrane, then 150 to 200 millimeters of mineral wool insulation, a 25 to 50 millimeters air cavity, and finally a skin of clay brick. And if you found this video because you are buying a house that has a Rainscreen on it, and this is the wall that I've just described, buy it. You can stop here. Your grandchildren and even their grandchildren will thank you. If your wall is anything else, stay with me and we will explore what a Rainscreen is, how it works, and what can go wrong. Our story begins in ancient Rome. 2,000 years ago, Roman builders faced a familiar problem. How do you keep the water out of the building? Their solution was simple and brilliant. They invented a system of roof tiles called tegula and imbreks. The tegula were flat tiles with raised edges. They formed the main surface. The imbreks were curved tiles that sat over the joints between the tegula. This created the first known baffle joint. It wasn't completely sealed, but it stopped most of the rainwater from getting through. Some water still made it past the tiles in heavy storms, and that was exactly the point. The Romans didn't aim for a perfect seal, nor they could possibly achieve it with the material technology at the time. They have allowed small amounts of water in, then built ventilation and drainage into the roof so it could run off or evaporate harmlessly. That idea, accepting some water ingress and managing it, is the foundation of Rainscreen design today. Modern roof tiles work the same way. Ask any tile manufacturer and they'll tell you no roof tile system is completely waterproof. Every one of them relies on underlayment and drainage. The Romans simply worked this out 2 millennia ago, and we have formalized it in today's building science. Aiming for water management is better than aspiring for perfect water exclusion. The same joint appears in modern facade standards from CWCT and NHBC. Now the imbreks is hidden behind the cladding joint, applied vertically instead of on the slope. In the warranty provider standards, it's still called a baffle joint. And that detail matters. With baffle joints, for example, the cavity behind the cladding can be as small as 38 millimeters. But if the joint is left open, NHBC requires at least a 50 millimeter cavity behind it. The Roman tile design is so good, is still in use today, virtually unchanged. But the question remained, could this principle work vertically on walls? Fast forward to 12th century Norway, meet the Stave church, the oldest surviving Rainscreen facade in the world. Built entirely from timber, it stands in one of the wettest regions on Earth, Western Norway. Western Norway sees over 250 rainy days a year. Annual precipitation exceeds 2,000 millimeters. So why hasn't this building rotten after 900 years? It is because the facade doesn't try to stop rain completely. It manages it. Vertical timber boards hang from the structural frame. Behind the boards is an air gap. Moisture that gets in can drain and evaporate quickly. The structural frame sits behind the space, protected from the direct weather. And the rainscreen is only part of the strategy. Wide roof overhangs throw water away from the walls. Carefully shaped sills and ledges stop water from lingering. It sits on elevated, well-drained ground. The church stands on a stone foundation that lifts the timber clear off the ground, moisture and splashback. All these factors work together. The rainscreen is one element in complete water management system, but it's a crucial one. Without the ventilated cavity, even the best overhangs wouldn't prevent moisture buildup. Stave church proves timber buildings can last for centuries in wet climates. And the key isn't total exclusion, it's moisture control. This Norwegian insight spreads across Northern Europe. And half a world away, another culture was arriving at a similar idea in its own way. Centuries after Norway's Stave church, Japan's carpenters developed their own way to keep buildings dry. By the late 16th century, a style called Tsukuri, and I really hope I pronounce it right, emerged from a tea house culture. It blended elegance with practical climate-smart detailing. Japan's climate is tough, hot, humid summers, cold, damp winters, heavy seasonal rains, and occasional typhoons. The structure was straightforward. Timber posts and beams set on stones, lifting them clear of splashback. Between the posts, builders wove bamboo lath and coated it with earthened plaster, probably the first known vapor control layer. These infill walls could release moisture instead of trapping it. White eaves sheltered the wraparound veranda, keeping most of the rain off the walls. Then came the secret weapon, the amado, sliding rain doors that ran on tracks outside the main posts. In bad weather, the amado, the sliding doors, closed to form a protective outer skin. When the skies cleared, they slid away into storage. It was in effect a movable rain screen in front of a breathable wall. The principle matched Norway's approach. Don't fight the moisture, manage it, keep most of it out and let the rest dry quickly. The Industrial Revolution brought new materials and new challenges. By the mid-19th century, British builders had introduced a more sophisticated version of a cavity wall. This wasn't just two walls side by side, it was an engineering water management system. A typical Victorian cavity wall had two leaves of masonry, an inner leaf of a cheaper brick or block, an outer leaf of a higher quality facing brick. Between them sat a cavity, usually 50 to 75 millimeters wide. Here's where the Victorians got clever. They used cast iron ties or S-shaped glazed bricks to connect the two leaves. The shape wasn't for decoration, it was for drainage. Glazed bricks were formed so water running down the cavity face would be directed back to the outer leaf. Cast iron ties had a deliberate droop or a twist in the middle, creating a drip point halfway along. When water penetrated the outer leaf, it would run down its inside face. If it reached the wall tie, the S-shape or drip notch would force it to drop harmlessly into the cavity, where it could drain away through weep holes at the base. The principle hasn't changed. Modern warranty standards still require wall ties to slope towards the outer leaf, with drip positioned to break the water path. Victorian builders added other moisture defenses, which are still used in today's brick walls. Cavity trays at floor levels, stepped flashings around openings, damp-proof courses to stop rising moisture. It worked. Many Victorian cavity walls are still performing well after 150 years. And this is when the Rainscreen went truly global. The system spread through the British Empire, from the damp winters in Britain to hot summers of Australia, proving Rainscreen principles worked in almost any climate. From medieval timber to engineered masonry, the cavity wall was now a proven performer. But the biggest leap was still ahead. By the beginning of the 20th century, Rainscreen principles had already proven themselves. Victorian cavity walls worked brilliantly. Two lifts of brick with a cavity between them. The outer brick didn't have open joints, just weep holes at the base. It relied on storing water in the porous brick, then releasing it slowly as it dried. simple and reliable. And the Rainscreen solution was widely used in timber cladding and double-leaf masonry. There were whip holes, but the joints between the bricks and timber planks were closed. And the early 20th century brought a new obsession: perfect barriers. Architects tried to seal entire facades in metal and glass. Unlike brick and timber, these are water-impermeable materials. The goal was to stop every drop of water with sealed joints. And it didn't work. Seals failed, water got in, and because there was no cavity, no ventilation, it stayed in, causing corrosion, rot, and stains. Then, in 1953, Pittsburgh Alcoa building changed everything. It had an all-aluminum facade over a steel frame. But unlike the perfect barrier systems, the joints weren't sealed tight. They were designed to let the air into the cavity behind the panels. This was pressure management. When wind hit the building, air moved through the joints. That reduced the pressure difference across the outer cladding. With little or no pressure pushing water inwards, far less got through. Any that did enter drained harmlessly out at the bottom. The goal was to keep the structure dry, and it worked. The building stood for decades without major water-related problems. However, the Alcoa building didn't have insulation in the cavity. Thermal performance wasn't the priority just yet. The Alcoa building showed us that managing water and pressure works. But in the 1980s, Vancouver went the other way. The city was booming, developers built fast, budgets were tight, and proven Rainscreen principles were pushed aside for a modern shortcut. That shortcut was the face-sealed wall. Most often that was eaves and insulated render systems directly fixed to the insulated stud walls. The entire wall was designed as one sealed barrier. No cavity, no ventilation, no pressure management. On paper it looked clever, lightweight, energy efficient, cheaper to build. But in real life, it was a trap. The water got in from the outside through the cracks in render, failed sealants, and tiny gaps around windows. But it also came from the inside. The water vapor moved into the wall from the inside of the building. When it hit the cold outer layers, interstitial condensation formed inside the stud wall. With no drainage and no airflow, that moisture stayed trapped. As a result, we got mold, rotting timber framework, corroded metal studs, and the structural strength of the stud walls quietly dissolving away. Some of these buildings were less than 10 years old when the damage was discovered. Entire neighborhoods were affected. The bill was over 4 billion Canadian dollars. It became known as the Leaky Condo crisis, and it was a turning point. British Columbia changed its building code. From mid-90s onwards, multi-storied housing had to be built with Rainscreen systems, a ventilated cavity, a drainage path, a second line of defense. The lesson spread worldwide, and Rainscreen thinking began appearing in other facade systems too. Precast panels added two-stage silicon sealant in their joints and weep holes in the outer seal. Curtain walls used two-stage rubber gaskets with built-in drainage. Almost all modern facades feature some form of weather management within the assembly. The industry has learned, yet again, the same truth that Romans and Norwegians already knew. Don't fight every drop of water, manage the water once it inevitably gets in. Next came the question, if Rainscreens work so well, how should we arrange all the performance layers, air, water, vapor, and thermal for maximum durability? That's where the perfect wall comes in. Sometimes after Vancouver's disaster, building scientist Joseph Lstiburek popularized the idea of the perfect wall. He didn't claim it was new. In fact, he admitted these walls had been used for decades. What he did was explain why they work so well and why we should build more of them. Here's the concept. All the control layers go on the outside of the structural wall, from the inside out. First, the structure, timber or light steel frame, or ideally concrete or masonry. Next, a continuous air and water barrier. This stops outside rain and stops inside moisture from moving into the wall. Then, continuous insulation. This is the thermal control layer. It keeps heat during winter and out during summer. It also keeps the structural wall warm, so there is no condensation risk. After that comes the cavity, a ventilated gap that drains any water and allows drying. Finally, the Rainscreen cladding, the first line of defense. It doesn't need to be perfect, it just needs to keep most of the water out. The magic is in the order. The structure is always warm, always dry. The barriers stop moisture from both directions. The cavity manages any leaks that get past the cladding. It is very forgiving. Each layer has its own clear job. If one layer has a small failure, the others still protect the building. The perfect wall works in any climate, hot and humid, cold and dry, or wet and temperate. It uses standard materials, it's simple to build, and it's easy to adapt. You can choose how much insulation to add. The cladding can be anything: brick, timber, metal, fiber cement, or terracotta, virtually anything you like. This idea became a gold standard for the Rainscreen design, influencing building codes worldwide. By the early 2000s, Rainscreen cladding was everywhere. It had become the default for multi-story buildings worldwide. And why not? Rainscreen is very forgiving. They worked even when the detailing was poor, and they often survived sloppy workmanship. The perfect wall idea wasn't just a fix for Vancouver's leaky condos. It became the go-to retrofit for aging precast concrete buildings from the post-war era. Those facades were already airtight and great for acoustics, but they looked tired and they lacked insulation. The retrofit recipe was simple. Cover the concrete with a breaded membrane, add insulation, create a ventilated cavity with brackets and rails, finish with decorative cladding. It worked, but success bred complacency. Quality control slipped, competence eroded, corners were cut. And Grenfell Tower showed where that could lead. Built in 1974, it had a concrete frame and precast cladding panels. In 2014, it was renovated with a Rainscreen system, insulation on the outside, ventilated cavity, and the outer cladding layer. The layout followed the perfect wall logic, but the materials and their arrangement were deadly. The insulation was combustible. The aluminum composite panel had polyurethane core, essentially solid fuel. The cavity that made the wall so good at shedding the water also created a perfect chimney for fire. On 14th June 2017, a kitchen fire raced up the facade in minutes. 72 people died. The Rainscreen principle wasn't the problem. It was the misapplication, ignoring fire safety. That tragedy forced the industry to remember the same cavity that drains water can spread fire just as efficiently. Fire safety in Rainscreen depends on compartmentation. Vertical fire barriers made from compressed mineral wool stop flame and smoke from racing around the building. Horizontal barriers stay open for drainage and ventilation, but include intumescent strip that expands in heat to seal the gap. There are other designs, like metal flashings, but these act as thermal bridges. They harm energy performance and will likely vanish from future buildings as thermal codes tighten. If you want the full detail, IAST offers dedicated facade fire safety courses, and our Facade Intelligence platform holds best practice details and case studies. Let's pause the history for a moment and look at how the modern Rainscreen work, starting with structure. Most of modern Rainscreen facades are non-load bearing. They don't hold up the building, but they must hold themselves up and resist wind loads. All forces are transferred back to the main structure through the brackets and profiles. These connections must cope with movement, thermal expansion of the cladding, deflection of the main frame, even seismic shifts in earthquake zones. Heavy cladding, like masonry, stone, or clay brick, needs robust brackets fixed to the slab edges. They are laterally restrained to the backing wall with brick ties. Lightweight panels or lighter materials like brick slips and terracotta tiles could be suspended by simpler brackets from secondary members such as stud walls. These brackets are typically made of aluminium, very thermally conductive material, and they create thermal bridges, paths of heat to escape. Modern systems use thermal breaks, insulating paths that stop heat flow while keeping the connections strong. Brackets also set the cavity width too narrow and the water can bridge across, too wide and costs will rise. Dr. John Straub research showed that even 6 mm gap can drain water, but bigger cavities allow for installation tolerances and movement. That's important because real buildings' frames aren't perfect. UK concrete tolerances, for example, can be ±10 mm. The brackets must adjust to keep the cavity consistent across the whole facade, meaning that the brackets have to accommodate tolerances up to 20 mm. Most designs use 38 mm cavity for baffle joints and 50 mm for open joints, enough for drainage, ventilation, and construction tolerances. Rainscreens control sound through two main strategies: mass and separation. Old masonry walls relied on just mass, heavy bricks that blocked noise. Rainscreens are lighter, but careful layering can match or even outperform traditional walls. The outer cladding is the first noise barrier. Dense materials like brick veneer or stone work best. However, open joints can let some sound through. The cavity breaks the direct path for structure-borne sound. The insulation, especially mineral wool, absorbs mid and high frequencies. Then the structural wall adds mass and stops what's left. In stud walls, thick sheathing board and even thicker multiple layers of acoustic gypsum boards do the heavy lifting. The biggest challenge is flanking transmission, sound traveling around the wall through other elements. Just like in curtain walls, backing studs are the weak point. The solution is often simply splitting the stud wall tracks and separate the gypsum and sheathing boards so they don't bridge between neighboring apartments. Despite the tragedy at Grenfell caused by systematic incompetence, Rainscreen systems remain one of the best retrofit strategies for existing buildings. Many older buildings leak energy, suffer from moisture issues, and look tired. Traditional retrofits work from the inside, add insulation between studs, upgrade heating systems, replace windows, but these often create new problems. Interior insulation could trap moisture inside the walls. Airtight buildings need costly mechanical ventilation. External Rainscreen retrofits solve all this at once. First, thermal performance. Continuous external insulation cuts thermal bridges and heat loss. Second, moisture control. The new weather barrier stops water getting in while the ventilated cavity dries out what's already there. Third, appearance. A dull, aging building can become architecturally striking with new cladding. Think back to Norwegian Stave church. Its timber has survived 9 centuries because its facade managed moisture. The same principle applies today. Buildings can shed their skin like a snake, keeping the structure safe while updating the outer layer for new needs. Just a few hours' drive from that church stands the world's tallest timber building, a 18-story, 85-meter hotel made entirely from mass timber. Its structure is protected by Rainscreen cladding. As carbon targets tighten, timber structures with Rainscreen protection will be part of the answer. And then there is housing and skills crisis. We need to build more, taller and faster. The answer will be prefabrication. And Rainscreens are already part of it. Look at unitized curtain walls with decorative finishes like terracotta or brick slips. Those finishes are essentially Rainscreen cladding fixed to the perfect barrier facades, which serve as a backing wall. Rainscreen as a water management strategy is so successful, it will definitely form the solution for the new challenges in the building industry. If you have enjoyed this exploration in Rainscreen cladding, make sure to subscribe to our channel for more deep dives into facade engineering. Check out our other videos on curtain wall, precast concrete facades and insulated render systems. If you want to dive deeper into facade engineering, visit the Institute for Architectural Science and Technology website. We offer comprehensive courses on Rainscreen design, building physics and facade engineering fundamentals. Many of our introductory courses are available free of charge. And the 3D models and technical drawings from this video are available on our Facade Intelligence platform. Subscribe to the free plan to access these resources. And we will see you in the next video.